Thank you, Michael, for the introduction. And good morning. And I'm going to present two sensors for environmental monitoring. First sensor is biomimic and chemical sensor. Another one is graphene-based chemical sensor for the air pollution measurement. Okay, and first sensor, we call them MEMS chemical sensor with bio-inspired electron array for enhanced lead detection. Of course, we can also detect, another heavy metal ions like copper and zinc as well. And second sensor is based on the chemically functionalized 3D graphene hydrogen for high performance gas sensing. And this is the first sensor I'm going to present. And the motivation is described here. And conventionally, normally we have to take a water sample from the river or reservoir. And so when then they transport the sample to a laboratory, and so the analysis will be done in the laboratory with some facilities set up. And finally, we can get a result. And this procedure actually is very time-consuming and also need a labor-intensive sampling collecting task. And also during the transportation of the sample to a laboratory, maybe some, the predictable reaction happening, and also may cause some, the contaminations. And of course, all experiments should be supposed to be done in a central place. Also it requires, the well-trained personnel to operate such a, sometimes a very expensive machine. And also this is because we're working very close with Michael, and in terms of this inspiration, biomimic and stuff. And so we just learned from the, this shark. And in the shark, you have this, the olfactory organ here, and this inlet and the outlet. And the water when enters this area, and this is the olfactory rosette here. And you can find many here nanoscaled sensing element, and they called sensory epithelium, this area. So, based on that concept, we designed this kind of device, and this MEM device, and we have the microchannel, and this inlet will come into this the detection areas, and with three the electrode. One is the working electrode, another one counter electrode. This is the reference electrode. And so then the water coming in, the spread, and the actual microchannel guides this kind of water into this is the measuring area, and with the micro pillars called. And so the reaction we have here, you can measure the voltage, or current, whatever. And finally, the sample comes out from here. Okay. And of course, very similar, the shape very similar to the olfactory, rosette of the shark. And also, this micro pillar is very similar to this standing cilia in the sensory epithelium. Okay. The purpose is actually to increase the sensitivity of the sensors. And this is a fabricated device. And of course, here the size is quite big, but actually the reaction, the part of the sensor, very small. And see, because we do the soldering, and for the, the electrical connection, this is why the whole chip size is quite big, but actually the core, the chip area is very confined in this area. And of course, this is a micropillar and electron array, and this is the whole the reaction area. And the size here is 500 micrometer. So we carry out the testing, and we compare, the concept about inspiration with micropillar without micropillar. And because the increased area of the micropillar, which enhance the reaction. So we found this is about 30% increment of sensitivity. And actually, of course, we can miniaturize further this micropillar down to the nano scale, and the sensitivity could be increased further. Of course, it's also the more measurement result showing that with increased flow rate and also sensitivity, the current we measure here also increases as well. And we have done also a range of the testing, and for this phone, of course, for the ladder detection, and with various flow rate and this potential and the voltage applied during the measurement, we scan the voltage from minus 0.8 volt all the way to 0 volt, and this peak represents this actually spectrum of the heavy metal of lead. Okay, and of course, actually the sensitivity quite high, and also we just draw this linear line and by the versus concentration of the sample, and shows a quite linear response. Okay, and we also fabricate microchannel in the device, and compare the sensor without a microchannel with microchannel. Then you can see the performance of the sensor have been increased a lot, and in terms of the measurement time, much shorter with the microchannel, because all the sample confined in the microchannel, and you can isolate the reaction actually. And also, the detection range also extended as well. And this is 10 to 100. This is here, then one order more. And also the sensitivity, okay, and increase as well. And this is nanoampere. This is the current we're measuring. So, almost double, 10 times higher, more than 10 times higher. And also limit detection was important for the sensor, chemical sensor, and we can reach 0.2 ppb, okay, the range. But practical use probably is sensitivity too high already. So, but anyway, okay, the second one, the sensor I'm going to present is called chemically functionalized 3D graphene hydrogen for high performance gas sensing. And of course, the graphene is very, the hot the material being researched. And we try to use this graphene material for our gas sensing, because it's a special, the property of the graphene material itself. And this, of course, this now we are doing the sensor for environmental monitoring in the air, so it's different from the water. So, but however, in the air, of course, normally you see such gases, NOx, NO2, O3, and SO2, and CO, and also ammonia as well. And of course, this is also a very toxic gas, and will affect our health and also environment as well. And so graphene, okay, this is structured micrographene. It's a very narrow scale and has, some specific advantages in the chemical sensing, and because the atomic and two-dimensional conjugated structure you can see here, and larger surface area, sure, yeah, and low noise level, and this in terms of electrical property, and also high electron mobility. This also enhances the sensitivity as well, and also has sensitivity to gas molecules. The detection principle, general, is quite simple, and we place two electrodes, and if this is graphene, here place one here, and so we can measure, called conductivity. Actually, this is, we apply voltage, you measure the current, how much. So, And so, of course, general resistance change of graphene exposed to gas. If the gas reacts with graphene, the change of the actually resistance, and the reason actually is the electron transfer from p-type graphene to electron withdrawal. This is NO2 molecules lead to increased charge carrier, which is a hole in the material concentration in graphene, leading to reduction of its electrical resistance. Okay, and this is our device. And so we have done a lot of research before, using the microheater. And we started a few years ago using concept for the airflow measurement together with Professor Norford. And now I apply this technology to this gas sensor using the graphene. And the microheater, actually, we try to increase the temperature because as long as you can have a high temperature, normally reaction is faster, also stronger. So on top of that, we put this interdigital electrode and place two electrodes here. We measure resistance here, between this one. But we place this so-called 3D functionalized the RGO, hydrogen, the graphene material. On top of that, bridge, the connection between the digital electrode. Yeah. So, of course, this is a special technology we developed by Dr. Wu Jing, and it's called 3D chemical functionalized reduced graphene oxide hydrogen material. Yeah, it's a very special material we use here. And this is as in picture showing the 3D, and it's just not one sheet of graphene. It's quite bulky graphene, and so you have enhanced surface area in the case. And this is the interdigital electrode. We place this graphene on top of that. Okay, you see the graphene here, and so we measure also the current versus voltage, and also SRD spectrum confirms this formation of 3D graphene hydrogen. Okay, and we did this test in the gas chamber, and we, the gas we use here is NO2, and previously actually we had done this RGOH only. It's not functionalized, and we compare with our previous result by using the chemically functionalized, the RGOH. Actually, the sensitivity, response time, response speed here increased by twofold. Yeah, twofold. And also, because response time is very important, another one also, the recovery speed is much faster. And sensitivity increased as well. And of course, this is the previous result we done last year, and this is the result we done this year. Okay, and so as I mentioned before, actually we started about 2 years ago, and with graphene-based concept for the gas sensing, and previously we used 2D RGO, reduce the graphene, the outside the sensor. Then we moved to the 3D and RGOH. Now we use the functionalized 3D, and you can see the sensitivity increased a lot. Increased a lot. This is 3D, and this is done at a temperature 22 degrees here, and in the 38 degrees, and you have the reduction of the sensitivity a little bit, but not too much. And you can compare with CO2, and which is sensitive to the temperature. And for the chemical sensor, actually very important, you have two properties, very important for the sensors. One is sensitivity, another one is selectivity. So by increased temperature, you can suppress the detection of another gas, but you can select the special gas you want to detect. Yeah, this is the idea behind use this is microheater. And temperature-wise, not so high, it's 38 degrees only, and won't affect kind of environment, whatever, power consumption also very limited as well. Okay, I think this is all of my presentation. Thank you very much. By the way, for first, the sensor chemical, the laser detection sensor, we signed a so-called research cooperation agreement with local company, and the company is trying to evaluate performance of sensors. Eventually, we can move further for the commercialization. Yeah.
Thank you, Professor Miao. Questions?
We saw two models. One is you form the company yourself. The other one is you find the company. What is easier? How to do it?
Sorry.
What is easier, to form your own company or to go to another company and have them do the...
Okay. Of course, we have the different, the staff, research student working on the different project with the professor, also, Michael and Professor Norfolk. And so we have discussed the issue whether, if we have, so many sensors we developed so far, we think this is kind of, the cooperation, and we should put our sensor into one company, for commercialization, or we set another company as well. So, and also depend also is this VCs, fundings, and if a VC love to have all the sensor developed within the company, we're happy to do that. And for us, for me, I mean, it's better to all put all sensors into one company. It's easy to measure for the measurement. So, so far, still under discussion. So.
Any other questions? Okay, thanks again.
Yeah. Okay.